what we have here is a simulation created by Peter Kolengridge in response to one of our computer science challenges to show how many particles might interact gravitationally. And the whole point of the simulation is to get an intuition for how galaxies form, why they have the structures they have, how solar systems form, how they have the structures they have, and how gravity alone can kind of define that structure. And what's really interesting about the simulation, besides the fact that it's just mesmerizing and extremely cool, is it shows the particles collide. Once they get to a certain critical mass, you see that they get colored yellow, maybe to indicate that they are now a star. Fusion can now occur. And you can zoom in at different levels to really see how the different particles or the different masses are interacting. And then you can actually rotate that to see a little bit clearer. This is if I'm looking kind of right on top of it to see how they're interacting. And it's a three-dimensional simulation, so it's a very rich way of thinking about these. And what's exciting for me is it's highly dependent on what the initial conditions are. In an earlier version of Peter's simulation, he did not give a net angular momentum to the system. And so you did not have as much of kind of the planet satellite or as much of the disk structures forming, although right here we don't have too much of a disk structure, although it does seem to kind of, there does seem to be a dominant plane in this scenario. And what's exciting is here we have a binary system. Sometimes you restart it. You might not have a binary system. Depending on the initial conditions, you might have something that starts to look like the Milky Way. Sometimes you might have something that looks very different than the Milky Way. And it really gives us clues of why we see such diversity, especially in when we're looking at galaxies, the structure of galaxies, that it's highly dependent on initial conditions. One can argue that our own solar system did have some net initial angular momentum because the current theory is what really catalyzed it was a nearby supernova that sent a shock wave and allowed the dust that would form our solar system to reach a critical mass and start to condense into the sun and the planets. And so this isn't, at least in my mind, too unrealistic of a scenario, and it's really cool to look at, and it really gives you a sense of things. You already see you have a binary star, they're kind of orbiting around each other, or orbiting around the center of mass, which kind of looks like around each other. And then this star right over here has its own kind of captive planet that is just rotating around it. We can see it a little bit clearer. If we had at least from this perspective, a very close range, we can zoom in a little bit more to see it a little bit better. This has a satellite, but then they're also kind of dancing around each other. So it's a really fascinating simulation. I could really stare at this and play with it for days. And I encourage you to play with it, restart it, see how the initial conditions or what type of solar systems or galaxies you might end up with. Whether they form disks, whether you have binary systems or not, whether you have planets with satellites. And then if you are more advanced, actually play with the code and see if you can really change the initial conditions, the starting velocities of things, the number of particles and things, the distribution of mass that you start off with, the angular momentum that you start off with, and see how that might change the structure of the universes that you create. And I'm going to add an annotation to this video that links directly to this simulation, and I'll also put the link inside of the description. So have fun. I could literally spend hours with this. It's a fascinating module that he's created where you zoom in and out, and I really thank Peter Kolengridge for this incredible contribution.